So just a little bit about atomic masses. You're going to see these, you're going to see average atomic masses on the periodic table. Those are the numbers with all the decimal points. The unit for atomic masses is the atomic mass unit. Sounds pretty normal. This is based on carbon-12 being 12.000 atomic mass units. Right? So it is in reference to this specific atom. Okay, so that's one thing to understand about it. A proton, by the way, carbon-12 would have 6 protons and 6 neutrons, giving it a mass number of 12. But just to note, a proton, it's maybe close to 1 AMU, but it's a little bit higher. And same thing with a neutron. And if we multiplied these by 12, we'd see that this would be would be slightly larger than 12. So the reason for that, we'll save that for another time. But I want to point this out, right? A proton and neutron, although they are close to 1, right? We see 1.01, 1.007, 1.008, or 1.09. They are not exactly 1. So it is carbon-12 that is defined as having 12.000 AMU. You might ask yourself, well, how much should a helium-4 atom weigh? And helium-4 has 2 protons and 2 neutrons. It's the same ratio of protons and neutrons. Or you might ask yourself how much a magnesium-24 atom would weigh, which is 12 protons and 12 neutrons. And you're going to find that it's not some easy multiple of 12. So just real quick, so carbon-12 is 12 AMU. Helium-4 is 4.0026 AMU. And magnesium-24 is 23.9850 AMU. So these nuclei that are larger, the numbers are a little bit lower than we might expect. And for helium, which would have a nucleus that's a bit smaller than carbon, right? The nucleus is smaller. We find the mass is a little bit larger than we would expect. So I want to put this one on hold, but see binding energy if you're interested in this, and you really must know right now. Next thing, so isotopic abundance. So when we have atoms of different elements, they come in different varieties called isotopes. So one that's usually illustrated in textbooks is chlorine. Chlorine only has 2 naturally occurring isotopes. So we find chlorine-35 and chlorine-37, and that's it. It's nice. It's kind of simple that it only has 2. We have an abundance, so I've written that up here as 0.7576. If you wanted a percentage, it would be 75.76%. And then that's for chlorine-35. Chlorine-37 is, you see the atomic mass of it, and that's 0.2424 abundance, or 24.24% abundant. So we see that we've got about 3/4 is chlorine-35, and about 1/4 is chlorine-37. So the average atomic mass that we expect on the periodic table, we do expect it to be closer to chlorine-35's mass, because there's more of it. So when we find chlorine in nature, chlorine is always a mixture of chlorine-35 and chlorine-37, and these are the abundances we find. Okay, so when you look in nature, it's always 3/4 of one, 1/4 of the other. When we find the average atomic mass of chlorine, we take the abundance times the mass of that isotope, and then we take the abundance of the other and the mass of that isotope, and we add them together. So we get something like 35.453 AMU based on the numbers I have here. If you check your periodic table, you'll see 35.45. So these are 2 isotopes of chlorine. These are their masses. These are their abundances. And this is how we get the average atomic mass that you see on the periodic table. Just to point out, the masses that you see on the periodic table, not every element comes in more than one isotope. There are some elements that only have one isotope. You could say monoisotopic. Fluorine is one. Gold is another one. Oftentimes they are odd-numbered elements.